record to computer. Okay, so now this should be working. Okay, so we've been talking about obtaining parameters with their uncertainties from fits to our experimentally measured data. And so far we've talked about straight line fits, right? That's the simplest case. We've talked about polynomial fits. And today we're going to look at a case where we can't fit the data to a straight line or a polynomial, or in fact, any of the default functions that are available in standard spreadsheet programs like Excel. So we're going to learn a very powerful tool, and that is how do we fit parameters to a nonlinear regression for an arbitrary function. Can be any function that you want. And so I'm going to use as an example some data related to the lab where you're going to have to do this semester, so you can sort of directly see how it's going to work when you do this lab. And in particular, the experiment where you're going to need to do this is the experiment on the inversion of sucrose. And so that is, let me get a pointer here. Oh, maybe I have to go. Okay, I have to click here. Okay, laser pointer. Okay, now I can go back. All right, now it works. Okay, so basically, the experiment that you're doing is you're going to look at the kinetics of this reaction shown here, where basically sucrose, right? So the disaccharide sucrose is broken apart into its components, glucose and fructose, and this is an acid catalyzed reaction. And the way that you're going to follow the progress of this reaction is by polarimetry. So sucrose, glucose, and fructose, these are all sugars. And biological sugars are chiral molecules. That means they are different than their mirror image. They're not superimposable on their mirror image. And chiral molecules have the property of being optically active, which means that when you shine light through a solution containing a chiral molecule, you rotate the polarization of the light. So if you shine plain polarized light through a solution of sucrose, the light will rotate polarization, and you can measure this polarization rotation. Okay, so that's what you're going to do. And so in this case, the analysis of the data is a little bit convoluted because both the reactant, sucrose, is a chiral molecule, and the products, glucose and fructose, are also optically active chiral molecules. However, luckily, the polarization rotation due to sucrose is very, very different than the polarization rotation due to glucose and fructose. And in fact, it's in the opposite direction. So as this reaction takes place, the rotation angle of the light that you're going to measure is going to change significantly, right? Because you get rid of the molecule that's rotating it this way, and you add product molecules that are rotating the light the other way. Okay? And so basically, you're going to measure a data set that's going to be rotation angle versus time. And the reaction is going to follow pseudo first order kinetics. And you can get the rate constant by fitting your rotation angle alpha versus time t to this equation shown here. I'm not going to derive this equation right now. You can read about the derivation in the lab manual as you get ready to do this experiment. And then you'll understand where this equation comes from. But basically, it involves three parameters: alpha naught, alpha infinity, and k. K is the rate constant that you want to determine. And then these two parameters, alpha naught and alpha infinity, are the initial rotation angle, right, at t equals 0. And alpha infinity is the rotation angle that you would arrive at if you ran the reaction all the way to completion, right? So at infinite time, this would be the rotation angle of the products that are left over. But actually, this reaction is very slow, and you're not going to have time in lab to follow it all the way to completion. And so you're going to be able to measure alpha naught, which is the initial rotation angle. This is just due to the sucrose. but you're not going to be able to measure alpha infinity. So you're going to need to include that as a fitting parameter. So the fitting parameters are going to be alpha infinity and k. And so it's actually sort of really inconvenient that we don't know alpha infinity, because it gives us the second term over here in this equation that's unknown. And so you're probably used to having situations, right? We've seen this a number of times where you have some function, right? Some measured value y is equal to, let me put this so you can see it on the board. So y is equal to, some unknown prefactor a times an exponential of, maybe kt or something like that, right? If you have a function like this, then you can do the trick where you take the natural logarithm of both sides, and then you can plot the ln of y versus, so this is ln of exponential of minus kt, which of course is going to equal it's just going to equal minus kt, right? So then you could plot ln of y versus t, and you can determine, oh, sorry, this is ln a. Then you can determine the a coefficient from the y-intercept. You can determine k from the slope, right? But unfortunately, we don't have that situation right now. We have a situation where there's another constant added to the end of this expression. So if you have y equals, some constant times exponential of minus kt plus some unknown, alpha infinity. Now, unfortunately, it's not possible to do this trick where you take the natural logarithm of both sides, right? Because when you take the natural logarithm of a times b, then that's ln of a plus ln of b. But if you have natural logarithm of a plus b, there's no simplifying expression, right, where you can simplify that into a term and a b term. Okay, so we're going to have to do nonlinear fitting in order to determine these two fit parameters. All right, and so next I'm going to work that as an example. So we're going to use the solver in Excel in order to determine the best fit values of k and alpha infinity from the following data. So at each time, right, given in hours, minutes, and seconds, you measure the rotation of the plane polarized light, and this is the data that you get. And the measured value of alpha naught is 22.6 degrees. Okay, so let's do this example. Sorry, let me find my template. Oh, should have gotten rid of that. Okay, I'll zoom in a little bit so the numbers are a little bit easier to see. Okay, is that big enough to see? Should I do a little more zoom? Maybe one more time. Okay, so you've measured the time, reaction time in hours, minutes, and seconds, and then you have alpha in degrees. So probably, first what you want to do is calculate a more convenient format for the reaction time. So let's just calculate the reaction time in seconds. So I'll create a column here, reaction time in seconds, and I'll take the number of hours times 3,600, right? That's the number of seconds in an hour, plus the number of minutes times 60 seconds per minute, plus the number of seconds. Okay, and that should give me the reaction time in seconds. And then I'll drag down the formula. Okay, and What you might want to do next is just go ahead and plot your experimental data so you get an idea of what it looks like. So I'm going to insert a scatter chart, select data series, or select data, sorry, add data series. I can call this, I don't know, experimental data. And I'm going to select the X values, the time in seconds. And for the Y values, I'm going to select the degree of rotation as a function of time. Okay, so now it looks a little bit stupid. So probably I want to put the X-axis at the bottom. So I'll go to format the axis. And I'll put the X-axis, let's see, horizontal axis crosses at maybe -10, so it's at the bottom. Okay, now it looks a little bit better, but I'll go ahead and add some axis labels so that we know what we're looking at. So let's see, primary horizontal axis is going to be, this is the reaction time in seconds, and the vertical axis here, this is going to be, I could just call it alpha, and that has units of degrees. Okay, so you can see the initially measured value alpha naught, I'll just go ahead and put that here. That was what, 22.4, am I remembering correctly? Let's go back to the presentation. Oh, sorry, 22.6 degrees. Okay, so alpha 0 in units of degrees is 22.6. And maybe I'll put it right here. Okay, and so yeah, you can see that you sort of start out, maybe if you extrapolate back to 0, it looks like maybe 22 point something, so that looks reasonable. And then as a function of time, this rotation angle decreases, and then it becomes negative, right? So this alpha infinity value, if you kind of follow the trend, it's going to be some negative number. It's probably going to be a little bit less than the final value that we measured of, -7.6 degrees. But in order to fit this, we're going to use a solver to minimize chi-squared for the function. And in order to use a solver, first we need an initial guess for the function. So I'm going to go ahead and I'll sort of guess initial values for the 3 parameters, right? So the 2 other parameters that are going to be fitted, those are the alpha infinity. This is going to be in degrees. And we need to just guess an initial value. So, our graph stops at -7. It's trending downward. So the infinite time limit is going to be something a little bit less than that. I don't know, maybe -8, -9 degrees, something like that. That would be probably a reasonable initial guess. And then I'm also going to need to make an initial guess for the pseudo first order rate constant K. And this is going to have units of reciprocal seconds. And you might be able to look at this graph and sort of, based on the rate of decay, you might make an educated guess about what K should be. I'm just going to be really stupid and just guess a random number. I'll just say let's let K equal 1. Okay, but as long as you have parameters, then you can calculate the rate based on those parameters, right? So, or I'm sorry, the alpha based on those parameters, right? Because we have this equation. So let me show you the equation so that I copy it correctly into the spreadsheet. Okay, so here's the equation that we're using. Sorry, let me adjust this window. Okay, now you can see it, right? So alpha equals this thing down here. So I'll call this alpha fit in units of degrees. And that's going to be calculated based on the fit parameters, which right now they're just a guess. So this is going to be, we take alpha naught minus alpha infinity. So alpha naught minus alpha infinity times the exponential of minus the rate constant k times the reaction time in seconds. And anytime you take an exponential, you want the units, you want the argument of the exponential to be unitless. And so if the reaction time is in seconds, then you want your rate constant to be in reciprocal seconds. So that's good, that works out. So finally, I need to take this exponential and add another term. I need to add alpha infinity. So that's this guy here. Okay, and then I'm going to want to drag this equation down. So I need to make these references to the parameters static references. So I'm going to add dollar signs in front of the numbers and letters corresponding to these parameters, but not corresponding to the time, because I want the time to drag down along with the equation when I drag it. Okay, so now I think this equation should be correct. I can drag it down. Okay, now I see, okay, I have a so-called fit. It's just based on my initial guess, but at every single value of time, my alpha is minus 8 degrees, which is the limiting value of alpha that I chose for infinite time. So basically what that tells me is I chose a rate constant that's much, much too fast because the reaction has already gone to completion in 4 minutes and 10 seconds. So I didn't choose this number very intelligently. So I'm going to decrease this number. You want to decrease it by quite a lot because you want to find the right order of magnitude. So I'll just decrease it by a factor of 10, so whole order of magnitude. Okay, and didn't do anything. So it's still much too high. So I'll decrease it by another order of magnitude. I'll put 0.01. Okay, now these numbers change a little bit, but the reaction is still too fast. So it's most of the way to completion, even at the first time point already. So why don't I just try one more order of magnitude? Okay, and now I get numbers that are a little bit more reasonable. So now the value starts at 15 degrees. That's reasonably close to the initial value that we got in the experiment of 18, and then it ends up at something like minus 7.8. That's somewhere close to this value. Okay, so now these numbers are kind of close to being realistic. So the next thing that we need to do is we want to calculate based on this so-called fit, which is really just a guess, but based on this, what would be the chi-squared value? Because we're then going to use the Excel solver function to minimize the chi-squared, right? Minimizing chi-squared, that's how you always obtain a nonlinear regression or any type of regression. So in order to calculate chi-squared, first I need to take the squares of all the residuals, and then I'm going to add them up, and that's going to be chi-squared. So I'll make another column. I'll call this residual squared. The definition of residual is it's the actual measured value minus the fit value. So it's this guy minus this guy, and then I'm going to square it. And then I'll drag down the formula to get the residual of each of these measured data points. And next, I'm going to create a cell here where I calculate chi-squared. And chi-squared is just the sum of the squares of the residuals. So I'm going to take the sum of all the values in this column here. Okay, so the next thing that I'm going to do is I need to find the values of the parameters that minimize the value of chi-squared, and that is the condition for the best fit parameter. So I'm going to do that using the solver function on Excel, which can be found under the data tab. So you're going to go to data, and actually, so if you've never used the solver before, it might not be under the data tab. So actually, if I unclick the solver add-in, then it goes away. So if you've never used your solver, then this is probably what your Excel looks like, or something like this, depending on what version of Excel you're using. So in my version of Excel, in order to get the solver, I have to install the solver add-in. And in order to do that, I click on Analysis Tools, and then I click here where it says Solver Add-in. I click OK, and then it installs the solver. If you're using a different version of Excel, my recommendation is just Google, how do I get the solver add-in in whatever version of Excel I'm using, and you should find the information. Okay, if you're having trouble, your TA can help you. Okay, so now I've got the solver, so I'm going to click on the solver. The solver lets you maximize or minimize a certain value by adjusting parameters. That's exactly what we want to do in this case. And so the first thing that the solver is asking when I open up this window is it's wanting me to set the objective. The objective is the cell that you want to maximize or minimize. So in our case, we want to minimize chi-squared. So I'm going to choose, instead of L5, I'm going to choose J7, right? Because that's the value that I want to minimize. And then I want to do that by, let's see. I don't know why it's not showing me my cursor, but okay. I want to change the, oh, whoops. Okay, I screwed this up. I want to set the objective to J7. Okay, and then I want to change the variables. Okay, so now it's wrong. So I want to change these two guys. So I want to minimize chi-squared by finding the best fit values of alpha infinity and k. Okay, so now this is set correctly. You want to make sure that this guy here is set correctly. So you can either find the values of the parameters that maximize chi-squared or that minimize chi-squared, or you can find the values of the parameters such that chi-squared is exactly equal to some value. I don't know, here it says 0. I think that's actually, in our case, physically impossible for it to be 0, but we want minimize. Okay, so make sure that that one's set correctly. The next thing that you can do is you can add a constraint. So if you're getting numbers that are gibberish, then you might want to constrain the parameters. So for example, I could add a constraint that alpha infinity, right, which is this one, has to be less than or equal to the final value of alpha that we measure, right? Because it has a downward trend that, you know, the final value has to be somewhere less than that, right? So that would be a reasonable constraint to add. Whoops, I think I should have clicked OK. Okay, this one has to be less than or equal to this one. And if I click OK, okay, now somehow I created two constraints. I think they're the same. I'll delete it. Actually, I think in this case, I don't need a constraint, so I'm just going to get rid of it for now. There's also this option, make the unconstrained variables non-negative. At the moment, I'm not constraining any variables, and I actually want one of the parameters to be negative, so I'm not going to check this box. And then the final option is to choose the solving method. So these are basically, there's a list of algorithms that you can use to optimize the parameters. And I'll just choose the default, which is GRG nonlinear. Okay, so next I'm going to click solve. And my computer is going to think about it for a second. And then notice now these two parameters changed, right? This was initially -8, now it's -10.16. And also the value of chi-squared is now much smaller. It changed from 70 to 0.1. So now the solver came up with a result. It says the solver has converged to the current solution. All constraints are satisfied. So that sounds good. So I want to keep the solver solution. So I'm going to click OK. And actually, I'm going to run the solver again in just a minute. So I'm going to go ahead and make another set of cells. I'll call these the best fit parameters. And I'll just copy these parameters down here so that I can store them. Okay, and so that's how we obtain the best fit parameters. So in order to convince yourself that these are reasonable parameters, what you probably want to do is plot them on your graph so that you can compare the measured values to the values that you obtain from your fit parameters. So actually, the way that I've set this spreadsheet up, the fit parameter or the best fit gets automatically calculated, right? Because the best fit is calculated based on these parameters here, which have now updated to the best fit parameters. So, one way I could do this is just directly, I'm going to select some more data. I'm going to add another data series. I can call this one the fit. And I can take the X values from here, right? The reaction time, and then I can add the Y values that are now calculated by the equation using the best fit parameters obtained from the solver. And if I do that, then it looks like they agree very well with the measured data. The way it's displaying is a little bit stupid. So I probably want to format this data so that the fit is displayed as a curve instead of as a, oh, actually, wait a minute. Maybe I clicked the wrong thing. No, I think that's right. Okay, maybe I'm just in the wrong tab. Okay, here we go. Here's the right option. So I want a solid line and I don't want a marker. So marker options, none. Okay, so maybe this isn't really the best way to display the fit because it looks really disjointed, right? Because I'm only plotting 4 numbers. And so this thing that should be, sort of a smooth curve doesn't look very smooth. So if you really want your plot to look nice, I would suggest maybe don't do it this way, but you might want to actually calculate the fit at a more precise set of X intervals, right? So I want a smaller X interval basically to plot. So I could also, I can make another set of columns. I'll call one of them time in seconds and one of them alpha fit in degrees again. And now, I can start at 0 and maybe I want a time point every 2 minutes. So I could set the next value in this time column equal to the previous value plus 120 seconds. And now if I drag this down, then the formula will also drag down. So this one is now equal to the previous cell plus 120 seconds. So it's 240 seconds. And if I drag it down some more, I want to go until I reach a value of something like 6,000 seconds, right? That's the range that we want to plot. So now I've gotten to 2,000 seconds. So I need to drag a little bit further. 5,280. I'll keep going a little bit. Okay, 6,240. That sounds reasonable to me. Okay, and now I want to take this equation that we obtained from here. I'm going to copy that over to here. The static references to the parameters, I think those get copied over correctly, but the time column, now it's H2, that's not correct. So I want to change that to L2. Okay, so now I can drag this down. And now I've got a fitted function, with a smaller time interval between each point that I've calculated. So now I'll add this to the graph. So I'm going to select data. I'll call this the fit. I'll select the time values here. And now I'll select the Y values, right? That's just the calculated fit. Okay, and now it looks stupid because it's plotting points instead of a curve. So I'm going to set it equal to, on the data series options, I'm going to set a solid line and no markers. Okay, and now we have a really nice looking plot, right? So we can see our measured data points, and we can see a theoretical curve through the data points, and it looks like it has very nice agreement. Okay, so that's basically the end of this example. So I'll go back to the PowerPoint quickly. And I'll start it again. Okay. So we've talked about how to obtain the best fit parameters for an arbitrary function. But what we have not done yet is reported an uncertainty or calculated an uncertainty in those parameters. So that's what we'll talk about next. In my research, if I was going to do a nonlinear fit to an arbitrary function, I would probably use some sort of software other than a spreadsheet program like Excel, because there are some nice programs out there that will automatically calculate errors for you. But we're going to use Excel because I think that's readily available to all of you, and you know, it's free. You're familiar with it. You know how to use it. And so we're going to use a method for error estimation that's a little bit more laborious. It's a little bit of a brute force method. But in this case, it's very effective. It's going to give you a very reasonable estimate of the error. And so this is called the Jackknife method. And basically, a Jackknife estimator for a particular parameter can be found by systematically leaving out each of the n observations one at a time. So you take your data set, you cut away the first data point, and you analyze it to obtain the best fit parameters. Then you repeat the process, but you leave out the second data point. Then you repeat the process, but you leave out the third data point. And then for each n data points, you're going to get a different set of best fit parameters. And you can obtain the uncertainty by analyzing the deviations in those parameters. So yeah, the uncertainty in the parameter can be obtained from the standard deviation of the repeated calculations of the parameters using the Jackknife method. Okay, so the sort of a cookbook recipe for how to use the Jackknife method. First, you're going to use the Excel solver to find the best fit parameters. You're going to do it n times. On the first iteration, you leave out the first data point. On the second iteration, you leave out the second data point, etc. Next, you're going to have a list of fit parameters. From that list of fit parameters, they're all going to be a little different because they're based on slightly different data sets. You're going to calculate the standard deviation of those best fit parameters, right? Those list of repeated k values and alpha infinity values in this case. And then finally, in order to obtain the 95% confidence interval, right, instead of the standard deviation, you're going to do that using the standard formula that you're familiar with. So that's calculated by taking the student t-value times this standard deviation that you obtained divided by the square root of the number of measurements. And here the number of degrees of freedom is going to be the total number of measurements minus the number of fit parameters, which in our case, the number of floated fit parameters is 2, right? It's just k and alpha infinity. Okay, so the final example that we're going to do is we're going to use the Jackknife method to obtain the uncertainty in the nonlinear fitting parameters obtained in the previous example. So let me exit the PowerPoint. I'll go back to the Excel spreadsheet. Okay, my computer has to think a little bit. Okay, I'm going to take this data over here. We don't really need to see that. I'll just move it over here. Okay, so now what we need to do is, so you know, maybe the first way you would think of to do this is, you know, make a new sheet and repeat the process, but delete one data point at a time. That would work, but there's actually a faster way to do it. What I'm going to do is I'm just going to create a new column. I'll call this maybe the Jackknife chi-squared. And I'm just going to set this column equal to the chi-squared value that is calculated using all 4 residuals, right? So the residual associated with every single data point. And I'll make that a static reference. So I'll put $signs here. And then I'm going to subtract from that the residual associated with the first data point. And if I enter, so now this value here, this is basically the chi-squared. So it's this plus this plus this plus this, but minus this. And so therefore, it's only this one plus this one plus this one, right? Because we've gotten rid of the first one. So this is the chi-squared value if you ignore the first data point. And now I can take this formula, copy it down. The second one should be chi-squared minus the second residual squared, right? So this is the chi-squared that you would get if you ignore the second measurement. This one's going to be the chi-squared that you would get if you ignore the third measurement. This one's the chi-squared that you would get if you ignore the fourth measurement. And so these are the values that we're going to want to minimize in order to apply the Jackknife method. And so let's do that now. So we open up the solver. So now the solver objective is set to this cell here, which is the overall chi-square. That's not what we want. We want this chi-squared. So this is the first chi-squared that we're going to minimize. Let me just check that the variable cells are set correctly. Okay, so I'll just use these same cells right here. And hopefully this will work without having to set a constraint. So I think everything's set correctly. It's set to minimum. This box is unchecked. We're using GRG nonlinear, so I'll click solve. Okay, I get a solution. It says it's converged. I get values that are similar to these values, but a little bit different. So I'm going to copy these values over here so that we know what values we obtained from the Jackknife method. And then I'm going to repeat the process. So now I need to repeat the solver again, except now I'm going to minimize this second value of chi-squared, which ignores the second measured set of values. So if I solve again, now I get a solution that's again slightly different. And by the way, this is only displaying one significant figure, but that's just because the width of the column is set too narrow. So it's actually calculating a lot more digits than that. Okay, and then I just repeat. So, for the purposes of illustration, I'm only using a data set with 4 measurements. Your data set is going to be a bit longer, so you're going to have to repeat this a number of times. But once you get the hang of it, it's pretty quick. You just repeat the solver using a different reference cell for the, which cell to minimize. Okay, so I've done it 3 times. I just need to do it 1 more time, and then I'm done. So finally, I'll set the objective to the last chi-squared value, which is this one. Solve 1 more time. Okay, and then I get 1 final set of parameters. Okay, so now I want to do statistics on these fit parameters that were obtained using the Jackknife method. So I will label the next row standard deviation, and I will calculate the standard deviation equals stdev of these repeated determinations of the alpha infinity parameter. And if I just drag that formula over, then I should get the standard deviations of the measured or the rate constant. Okay, and then in order to obtain the 95% confidence interval, I need to plug in the formula for that. So the 95% confidence interval is going to be the student t-value, which I need to look up. So let me go to my student t-value table. That's right here. The number of degrees of freedom is, there's only 4 measurements in this data set. So 4 minus the number of parameters gives 2. So nu is 2, so student t is 4.3. So I'm going to enter equals, sorry, 4.3, is that right? Yeah, 4.3. 4.3 times the standard deviation, divide by the square root of the number of measurements, which is 4. Okay, and then I'll copy this over. And now I get uncertainties for the fitted parameters. And that's how you're going to do it. Okay, and so if I was going to report these parameters in my lab report, how would I do that? Oh, whoops, it's somewhere down here. Here we go. So just so that you'll be able to see this in the video, I'll just type it right here on PowerPoint instead of going to the board. So I will insert an equation editor. So the final value of alpha infinity that you would report is alpha infinity, whoops, alpha sub infinity equals, okay, the best fit value is the value that you obtain using all the data. So that's these values that we copied down here at the beginning. So that's going to be minus 10.16 degrees, but the uncertainty is 0.5 degrees. So we're going to round to one significant figure of the uncertainty. So we're going to round to the tenths place. So alpha equals minus 10.2 degrees. Oh, sorry, minus 10.2 degrees plus or minus 0.5 degrees. And where's my degree symbol? It's up here. Okay, and then the other parameter that we've determined is K. So K, you're going to report that as, this is a pretty small number, so I think it's more convenient to use scientific notation. So I'll write this as 4.6 times 10 to the minus 4. But it's going to be plus or minus 3 times 10 to the minus 5. So the most convenient way to write that would be 4.6 plus or minus 0.3 times 10 to the minus 4, right? Because 0.3 times 10 to the minus 4 is equal to 3 times 10 to the minus 5. Does that make sense? And I've forgotten something. I need to add the units, otherwise this number is meaningless. Because rate constants typically have units, so the units here would be seconds to the minus 1. Okay, and then we're done. Okay, so that's it for the statistics portion of the talk. There's an extra credit quiz on Blackboard. And after you complete the extra credit quiz, I'm going to talk a little bit about expectations for writing lab reports. So if you go to the Blackboard page, it'll be on the home page. There'll be a quiz with today's date on it. The password for taking the quiz is solver. You get 2 points for a correct answer, 1 point for an incorrect answer. So please go ahead and enter an answer, even if you're not sure. And this is also how we know that you attend the lecture. Recording. And okay, so for the remainder of today, I'll just talk a little bit about expectations for, oh, this is not what I want. Let me go to maybe just full screen mode. Okay, I'm going to talk about expectations for lab reports. So this is the information, this is a rubric for the lab report. These are the elements that need to be in your short reports, right? Which is every lab report other than the Raman experiment, for which you only need to do a worksheet, and for the inversion of sucrose experiment, for which you're going to need to do a journal lab report. But all the other ones, you do a short report, and this is how it's going to be graded. So title, date of experiment, names of your lab partners, that goes at the top. That's 2 points of credit. You need to write a brief statement of purpose for the experiment. You get 5 points for that. You need to include your measured data. You get 10 points for that. If you took a small number of data points, right, by hand, then you can include a table that explicitly gives all the data points. If you used an instrument like the FTIR to measure a spectrum, right, it's going to collect thousands of data points. You're not going to list all of those. You're going to include your data in the form of a graph. But yeah, the measured data should somehow be visible in the lab report, either tabulated or in graph form. Then you should go through, so basically the person that's looking at this, they should be able to follow, how did you do your calculations? How did you use your measured data to come up with the final values that you're reporting and the uncertainty in those values, right? So the calculations need to be clear enough that, you know, your TA can follow what you did. The lab report overall needs to be typed, but if you want to handwrite the calculation section, that's fine. Finally, you need to have a results section where you present the numerical results. So you shouldn't make the reader dig through your calculations to find them. You need to have a final table that presents the final numerical results with the uncertainty. Next, you're going to have a discussion. Here you can discuss, for example, possible reasons for error, or you can maybe compare your values with literature values, talk about whether they agree. You need to include at least 2 references other than the lab manual. And then finally, as an appendix, you should include a photocopy of the relevant pages from your lab notebook. Okay, so I'll just show you quickly an example. So here's actually a 3107 lab report. Let me try to make this a little bigger. Okay, but it's in the same format. So so this is just an example of a lab report. This is on the bomb calorimetry of naphthalene. So basically you're combusting naphthalene in a bomb calorimeter, and you're using the temperature rise of the calorimeter in order to determine the heat of combustion of a compound. So, you know, date, names, etc. That's been redacted, but that's at the top here. The purpose of the experiment is given just very briefly, right? You're determining heat of formation of naphthalene based on the experimentally measured combustion heat. Next, the data is presented. So in this experiment, you would carefully measure how much quantity of sample you're combusting, and then you're going to present, okay, when we do the combustion in the calorimeter, what's the temperature versus time graph, right? And that lets you extract the heat of combustion. So here's weights that are reported very accurately, and then temperature versus time information for different runs. Okay, so then there's a thermogram, right, which is a graphical representation of the data. This helps the reader understand how the temperature rise was obtained from the data. And next, there is calculations and data analysis. So basically, the student explains how they obtained delta T by subtracting the final versus initial temperature. And then they explain how they got the uncertainty in delta T based on the standard deviation that they got from their fit to the initial and final temperature data. And then finally, they show how they calculated the calibration constant and the delta U of the reaction, right? That's all given explicitly. They always calculate the uncertainty. They always give the units. And then finally, they arrive at a final answer. This is their heat of formation for naphthalene. But then after the calculations, they present the numerical result, right? So this is the results. They give the main conclusions, which is they list the calibration parameter for the calorimeter. They give the molar energy of reaction, the molar enthalpy of reaction, and then the heat of formation of naphthalene, which was the goal of the lab. Okay, and then there's a discussion, right? So in this case, it's just a short discussion, just one paragraph, that's fine. It says the literature value for the heat of formation of naphthalene is about 617 kilojoules per mole plus or minus 7. And they obtain a value of 725 kilojoules per mole plus or minus 5. And so, these values are a little bit different, but are they in agreement or not? Well, 717 plus or minus 7, that indicates a range that could extend anywhere from 710 to 724, right? And 727 plus or minus 5, that would indicate a range from 722 to 730 or 732, right? So actually the uncertainty ranges overlap. So therefore, to within the 95% confidence intervals, the agreement is reasonable. Okay, then there's some references that are given, right? I think this is where they found the literature value. And then finally, there's an appendix where they show the relevant pages of their lab notebook. Okay, any questions about that? Okay, if not, let's keep going. Okay, so you're going to do a journal style lab report for the inversion of sucrose. This is worth more points. It's worth 170 points. The rubric looks a little bit different because you need to include some elements that are not included in the short report. So the first part looks the same: title, date of experiment, your names, your lab partner names. You need to include in the journal style lab report an abstract. I'll talk a little bit about that later. An abstract is basically a summary of what you did. It's the most important take-home message about what did you do and what are the main conclusions. In the journal style lab report, you need to include an introduction. This could be background material about the experiment you're doing. You could include a little bit of theoretical background. You could include motivation for why you would want to learn about this topic, right? Why is, the decomposition of sucrose an important reaction? Next, statement of purpose of the experiment. This can be similar to the statement of purpose in the short report. In the journal style report, you're gonna give the experimental procedure. This needs to be in prose format, so in sentence format, sentence paragraph format. It needs to be detailed enough that a competent scientist would be able to understand what you did and reproduce what you did. Okay, but you don't need more details than that. Okay, next, you're going to give results, data analysis and discussion. So basically you should include a description of how you analyzed your data, how you did the calculations. That can be similar to what you give in the short report. And you need to report the results, the main results in a table or in a graph. You need to include a conclusion. That'll be similar to the short report. And just like in the short report, you need at least 2 references, and you need to photocopy the relevant pages of your lab notebook in the appendix. Okay, so yeah, I'll just quickly go through this. So an abstract doesn't need to be long. It's typically 1 paragraph, 50 to 100 words. You're going to briefly describe what was measured, how it was measured. You're going to summarize the results and the significant conclusions. If the purpose of your experiment was to report a specific value, you might want to put that value right in the abstract so that people know, this is the most important thing that we did. We measured this value. This is what we got. Basically, the reason why an abstract is so important, it's kind of like a scientific TLDR, right? There's lots and lots of literature out there. Nobody has time to read every paper. If you're doing research on a particular topic, if you're trying to find a particular piece of information, you might try to find papers that are relevant to that. You're not going to read every paper, but you might take a look at every abstract of the papers that you find, and then it's going to tell you, oh, okay, in this paper, we measured this quantity, we found it to be this, right? If that's a quantity that you're looking for, then you might want to read the whole paper, figure out how they did it, and, is this probably an accurate way to determine this quantity? Can I use this information? Okay. Yeah, of course, if you include numerical results, you should also include the error estimates in the abstract. Okay, so the introduction should describe the purpose of the experiment. Why is it relevant? It can provide background on the experiment. You might want to include some information about previous experiments, right? When was the inversion of sucrose first studied? You want to, you can explain underlying theories that are necessary to understand the experiment, and so forth. Next is the procedure. You want to describe the sample preparation, describe the apparatus, explain how the apparatus was used to obtain the results. That's pretty much all you need. Next is the results section. You're going to present the relevant data that you collected. It should be organized so the reader can understand what data was obtained. You're going to use tables or graphs. Of course, you're going to label your axes. You're going to give the units. Otherwise, the reader doesn't know what any of these numbers mean if they don't have units attached to them. You're going to report the relevant observations and describe trends in the data. Yeah, and typically you don't want to include hand-drawn graphs. You want to use a plotting program such as Excel. Okay, data analysis. You want to describe how you analyze the data that you collected, provide sample calculations, detail the steps. Someone should be able to follow how you arrived at the final reported value that you get to. If you're obtaining a result that involves a fit to an equation, you want to include a graph somewhere in your lab report that has the measured data with the fit curve going through the data points. You want to show how the error was calculated. And if you made repeated measurements of your data points, then you want to show what is the error bar on that data point. Okay, and okay, next is the discussion. You want to include an interpretation of the data based on analysis, comparison of the results to literature values. You can explain sources of experimental error. In the conclusion, you can summarize the main findings. You can explain whether the experiment was a success or failure. And you could suggest improvements, right? What could you have done differently? What's a follow-up measurement that you could do in order to verify your guess as to why the experiment maybe didn't agree with the literature, and so forth. Okay, and then the references should follow the ACS format. And you should use either a numerical superscript or a number in brackets to refer to the reference from within the lab report. And so an example, so here's how you're going to cite a journal article. You give the name of each author, last name, comma, first initial. Then you give the journal. You can either use the full journal name or the abbreviated journal name. Next, you give the year, the volume, and the page number. And you can either give the full page range, or you can just give the first page. That's enough information for someone to be able to find the relevant article. If it's a book or a chapter in a book, you're going to give, well, in the case of a book, you're going to give, or I'm sorry, in the case of a chapter, you're going to give the author of the chapter. You're going to give the title of the chapter, then you're going to give the title of the book, the editor of the book, the publisher, the publication information, and the relevant pages that that chapter's on. If it's a book, you just give the author's title of the book and the publication information. Okay, and then here's links with more information. Okay, so I'll just quickly show you an example of a lab report in the style of a journal article. This happens to be exactly the same experiment that you're going to write about. Okay, so there's a title, name, date, abstract, right? So the abstract gives, it's fairly brief. It's just one short paragraph. It explains what was done in the experiment, and it gives the main results. It gives the best fit value for the rate constant and this alpha infinity. And then there's conclusions based on the that were drawn based on what the reaction mechanism is. There's an introduction and purpose section where they give some background information about polarization rotation. They give some background information about the reaction that they're studying. It's nice also to include some figures. They give a description of the procedure that they followed. They tabulate the results that they obtained. And let me kind of scroll down. Okay, they have, yeah, different fits that they needed to include. So here's one example, fitting the data to a second order fit. Actually, the conclusion is that the second order fit doesn't look very good. So it's a first order reaction and not a second order reaction. There's data analysis and discussion, and it's nicely typewritten. And then they give a final graph showing optimized values. Yeah, some final results. And then the conclusion. So in the conclusion, they basically summarize what the findings were, how successful the experiment was, what were the results that they obtained. Then they give some references. And there's some points taken off because there was no appendix. So they should have also included an appendix with pages from the lab notebook. Okay. Really quick, let's just finish this. Any questions? Okay, a few guidelines just on how to write when you're writing technical scientific documents. So the goal is, of course, to communicate what you did, why you did it, and what you found out. So you want to be as clear as possible, and you can also be concise. You don't need to write something that's longer than it needs to be for the audience to understand what you did. You want to write in standard English, avoid slang. You don't use contractions in formal writing, right? So you wouldn't use the word can't, you use the word cannot. The scientific literature is full of abbreviations. In fact, maybe there's too many abbreviations, but you always want to be clear about what abbreviations and acronyms refer to. So the first time you use an abbreviation or an acronym, you need to explain what it means. So for example, you could say, a calibrated flame ionization detector, parentheses FID, was used to determine the molar concentration. Then everybody knows FID means flame ionization detector. But standard things like SI units, everybody knows what this abbreviation stands for. You don't need to include that. Okay. Anytime you include a figure or a table in your text or in your document, you need to refer to it in the main text. So you shouldn't just include a figure that the reader has no idea what it is based on reading the text. So anytime you include a figure, you need to include a sentence in the main text saying something like, figure 2 shows a comparison of the data to the theoretical prediction of equation 3. All right. And then the figure, any figure or table needs to include a caption that explains what information is given there, right? And so the caption needs to explain, what the different things in the figure represent. So for example, you might want to include, black markers represent the measured data. The dotted line represents a least squares linear fit to the data. Okay. And you want to read through your lab report when you're editing it. You want to make sure everything is clear and that you're really saying exactly what you mean to say with each sentence. So just an example, how to improve the accuracy of writing. One sentence that I got recently from a research student said, the sample is heated by resistive heating and is switched off before the laser shoots. So literally this sentence says that the sample is switched off before the laser shoots, right? Because both verbs should refer to the same sentence. But what they actually meant was the sample is heated by resistive heating and the resistive heating is switched off before the laser shoots. So a clearer way to say that would be the sample is resistively heating and the heating current is switched off before the laser fires. Okay, you've probably learned a lot about passive versus active voice in your writing classes, especially in humanities writing. The active voice is very strongly preferred. In scientific writing, it's actually not unusual to use passive voice. It's okay to use passive voice in scientific writing. One of the reasons for that is that often we want to take the focus off of the subject that did the work, and we want to put the focus on the object, which is the experiment itself, right? The molecules or the material or whatever that you're experimenting on. But it's still good to use active voice if you can do so in a way that's clear and that places the proper emphasis. So it's good to use active voice. It's good to choose strong verbs. So, okay, let's look at some examples. Maybe you're doing an experiment. The gas sample can be let into the chamber by an inlet valve. So that's fine. There's no problem with that. But maybe it's stronger. It's better writing actually to say the gas sample enters the chamber through an inlet valve, right? That's actually a much better sentence to read. I would say that's clearer. I get the idea, immediately when I read the second sentence. Okay, passive voice is also acceptable, especially if it's used to avoid giving first-person information, right? So you wouldn't want to write in your lab report, Sally opened the gas valve while she may entered the equilibrium pressure in the lab notebook, right? Because that's too much information. The reader doesn't need that information in order to reproduce your experiment. So you can use the word we to get around that. We opened the gas valve and recorded the equilibrium pressure. That's fine. Or you can use passive voice. This is also a common alternative. The gas was introduced into the chamber and the resulting equilibrium pressure was measured. Okay. You want to avoid shifting tenses frequently. So within a given section, you usually want to stay in a particular tense. In the introduction section, you might use actually a mixture of present tense and past tense if you're giving historical perspective or historical background about a reaction or procedure. You might want to use past tense. If you're giving information that's generally true about why something's applicable, you want to use present tense, right? So for example, you might want to say calorimetry is a common technique for precise measurement of reaction enthalpies, present tense. The first reaction calorimeter was developed by Lavoisier in 1780. That would be past tense. Okay, the procedure, typically you would want to use simple past tense the whole time. So the sample was obtained from Sigma Aldrich and used without further purification, for example. The results and conclusion, usually you want to use present tense because usually the conclusions of a study should be true today, they should be true tomorrow, they should be true a year in the future. You're giving information that is in general true. So for example, you would want to say the results agree with the theoretical prediction to within the experimental error. Okay. Okay, I think that's all the sort of guidelines for writing that we have. And that concludes our lectures. A couple quick reminders. If you haven't done so yet, make sure you complete your safety quiz by tomorrow. Tomorrow at midnight is the deadline. Also, tomorrow is the last day that the CGSO is going to be giving out lab coats. So make sure if you haven't done it yet, go by tomorrow It's directly downstairs from where we are, down this hallway. Any questions? Yeah. Okay, maybe come talk to me after class and I'll figure it out. Any other question?